Florina, for introducing. I'm very happy to be at DefCamp again. Thanks for bringing me home every now and then for DefCamp. My name is Andrei Kostin, and I run the Firmware.re project, which is kind of a hobby of mine, and it's the result of my PhD studies for the last 3 years. And yeah, I'm a fresh doctor, but not the kind of which helps people, so that's why I don't put doctor in front. Today I'll be presenting InSecurity of embedded devices firmware, fast and furious at large scale. So it's a long title and it basically encompasses everything which I want to tell today and which I was researching for the last 3.5 years intensively and some years even before. So the idea is that we want to secure the insecure embedded devices, and we want it to do without devices themselves, which is more tricky, and we need to do it fast and quick and large scale, because we have a cloud. A very short who I am, but I'm pretty sure I don't want to brag too much. You've been seeing the MFAQ, or maybe you've used the MFAQ tool for RFID hacking, or RATB and Timișoara free transport rides, some hacking your printers in the office, getting the payslip of your manager from the printer, or maybe trying to get your airplanes down at the Ottopen airport, or looking on your manager through the CCTV cameras. This is kind of the research I've been doing, but everything what connects them is that they're embedded devices per se. So at a bigger scale, there are the printers and MFPs. At a medium scale, it's a CCTV camera, and a very tiny scale is the RFID, but all of them are kind of embedded devices. There's no interface, they're running small processors, there's some software which runs on them, and this software, which is the main interest of mine, is called the firmware. This is what I'll be talking about. So there are many security talks, especially this year at DefCamp, related to IoT security. I try not to use so much IoT, even though everybody tries to use it and is good, I think, but at the core of IoT, they're the embedded devices. And for many years, we know that embedded devices are everywhere, and they are becoming more everywhere, meaning they're in your house, in your office, in your drones, on your hands, in your headphones, and so on. They're everywhere. We know this, and we witness this every day. What we witness lately is that they are getting smarter and more complex, which means basically that they are not doing the simple tasks they used to do, like, I know, measure a temperature, and that's it. They are smarter and more complex, meaning that they run more complex software, meaning more complexity means more bugs, more security vulnerabilities. They need to support some kind of a cloud API or cloud connectivity. It means all kinds of API, RESTful, JSONs. All these are additional layers of software and additional bugs. And on top of this, that would be fine if they would be separated and just ruin your kitchen. But of course, when you connect your thermostat and your CCTV camera and baby monitor and your very smart vacuum cleaner with 360-degree CCTV camera inside, you want to control it from the office and brag on your smartphone, or you might do it for very practical things where you're traveling a lot and you really want to get hold of your devices and the state of your devices at home. So of course you want them to connect to the internet, and this is another big challenge to be solved. And usually you connect to them via some kind of a web interface so that you can easily click. You don't want to write very complicated shell scripts. You just want to click in a web interface and configure all of your devices. So besides that, on the other hand, we know that there is embedded software which runs on all these devices. So we've seen the hardware part or the devices part. And on the software part, the firmware is everywhere because they're diverse, but regardless of this, they need to run some kind of software. And in literature for embedded devices, it's called the firmware, and they run on your smart TVs, on your routers. Many of you maybe even updated your routers firmware, but I'm not so sure how many of you updated your hard drive or your smart meter firmware. Nevertheless, it occurs regardless of whether you want or maybe manufacturer want. So the firmware is there. So we have several observations to kind of motivate our study. In academia, it's really important to motivate your work. You cannot just go and start breaking things and say, hey, it's fun and let's publish this. We have some motivation, and the motivation to do this research at large scale, which I'll show a demo. It will not be only a boring talk, I hope. So back in 2014, we started the first collection, large-scale collection of firmware. So basically, we wrote crawlers which go on the internet, on support side, download side, and download the firmware packages, right? And we've seen hundreds of thousands firmware packages back in 2014. And this is just a small observable part, because some paths are restricted, some firmwares are not available on the internet, you need to order them, you need to buy a special SD card, you need to buy like a CD, a DVD. At the same time, like the number of firmware is huge, hundreds of thousands. Imagine you have to manually analyze hundreds of thousands of firmwares. It's not possible. I mean, for malware is also a challenge. So also in 2014, there were roughly, some predictions says 14 billion internet connected objects by the Cisco's Internet Things Connections Counter. There's a website and a blog where they periodically do this. And they do this counting based on some public infrastructure and private networks, because they have a big share in the networking equipment, so they can count and monitor these kinds of things. I'm not sure how exact is this number, and it's really hard to quantify, but you get the magnitude. Even if it's 1 billion, it's still a lot. 1 billion, 14 billions is billions, right? I mean, doesn't make too much difference. You cannot do them manually. And the prediction is go, okay, from 20 to 50 billion, it can be 100 billion, it can be 10 billion, but the idea is the same. So there's billions of devices and hundreds of thousands of firmwares. And this is important. These are kind of observations. We take them as facts because, well, we have to take some ground truth. And why securing them is important, securing the embedded devices is important, is because embedded devices, of course, you want to secure everything, but why particularly embedded devices? You don't use them so often. You can throw your router and buy another one for $30. But in general, as a principle, is if you think about this, embedded devices are ubiquitous. So basically, even invisible, they are essential to our lives. It can be like a heart pacemaker, and it's not easy to go and cut a patient every day because you forgot to secure a function. And okay, let's cut you another day because we need to upgrade your pacemaker. And some of them are in ECUs, in the cars, right? And they're also essential to our lives, because if your ECU is not functioning properly, then it's not very safe. It can operate for many years. For example, for smart infrastructure, it's buried in the concrete, in the cement, and you cannot just go and dig every day like 20 meters in the infrastructure just to get the sensors and update the firmware. And also they have like a large attack surface, right? So I mentioned particularly web interface, because usually these kind of home devices, smart home and IoT, you go and configure through the web interface, but there's some other networking interfaces, like for various purposes, for example, for video streaming, if it's a media server, also CCTV cameras. And basically, the idea is that there could be like debug interfaces to do servicing on these devices. And we can go through many examples. We've seen, starting from 2000, I think, examples of routers are the most preeminent examples, but there have been printers as well. There have been VoIP hacks on various Cisco and Nortel phones to do cybercrime and fraud on telecom networks. Cars, well-known research from 2013, which basically hit the news and the proof of concept this year. Drones are coming, and people are already playing with drones, hijacking their connections and updating their software. We've been showing also fireworks hacks last year at DefCon, and we show that this kind of system also can be wirelessly taken over and the firmware updated and so on, and this can be lethal and death kind of a question, not just fun. And the list can go on because every day you would see some kind of alert on a Twitter or on blogs that there's a new device or this vendor has another device which has hard-coded passwords. And the list can go on, but the idea is that each of these kind of results, examples of a blog post is a result of individual analysis. What it means is basically a researcher like me or you, anybody in the room, or like a group of researchers like Valasek and Charlie Miller. They sit for 1 month, 1 day, or 1 year, and they sit and do exactly the same process as any other person in the room. It can involve many manual steps. So is like individual analysis can take a very long time, and especially if it involves or includes a lot of manual steps. And the idea is that automation, we know, is a key, and that's why we write scripts and software, because we want really to automate things. And you can, if you read all of these blog posts which I shown you, and you go to any of these blog posts, you'll see that there's like chunks of steps which people just spend hours to describe, which can be automated in like 3 scripts command. And you can see the pattern that they repeat themselves on these blog posts every time. Just because people want to educate others how to do this, but you can also see the amount of manual work which is repetitive and doesn't make any sense. To give you an overview where is the manual process and basically where we can automate and help things out, I'll give you like an idea or a review of a simplified manual analysis process. And this is basically the core process which you'll see in many of these approaches, whether it's a router, whether it's a car, electronic unit, whether it's a smart card. Many of these steps are kind of similar. So the persons, okay, so there are 2 inputs into this process. One is you have a device and then you want to play with it and you get the firmware and you dump the firmware, or another, you don't have a device like me. I cannot have all the devices in the world, but I want to find vulnerabilities in all the devices in the world. What I do, I start with a firmware. But regardless of where you start, like with a device or with a firmware, essentially it boils down to taking the firmware, because you look in the software in the first place. Even if you have a device and you dump the firmware, you have a device exactly for the purpose of dumping the firmware in the first place. So you start with a firmware, or people start with a firmware, they try to decrypt it, and many pose us questions, okay, what do you do with the firmwares which are encrypted, because now vendors are getting smarter and yeah, they are putting encryption. And our answer is yes, we cannot deal with them right now, but our answer is we keep it. Storage is cheap, and in 1 year somebody will go with a JTAG on the device and will find the key, because the key is in the device or in some kind of storage, unless it's a smart card like which has tamper-resistant storage. But most of these IoT or embedded devices, especially cheap ones, they don't have tamper resistance, because tamper resistance costs 2 or 3 times the entire device, so they don't put it. So you just keep it there encrypted, and in 1 year you'll have the key and you can decrypt everything and you find all the files, right? So the encryption is actually not a problem, so we keep it. We cannot now, maybe tomorrow we will be more lucky. When we unpack it, what it means, we try to basically take, or people try to take the binary blob or the archive. They try to find different pieces of files or information. And usually people are trying to look for Linux kind of files, etc password for hard-coded passwords, and all kinds of other files or file systems. However, some systems can be different a little bit, and there is the tricky part. You need to know that you cannot unpack it, and actually it's a big blob or it's just a patch of a particular zone of memory. But the idea is that you unpack and you try to find building blocks of this firmware, and you end up with some files and some file systems and functions. Sometimes they come as iHex format, which if you translate to binary, you'll see binary patches and so on. Then is all the normal tools of reverse engineering come into place and testing. Like one is to try to detect the CPU. For example, if you have a device, yeah, it's so easy. Sometimes it's not that easy actually to open the device. If it's a router, it's easy. You open, you look in the device, oh, it's an ARM or MIPS. But if you have a Fitbit kind of a device, which is like glued and isolated, once you open it, it's broken. is broken, and sometimes also the chip is kind of obfuscated, is intentionally like scratched, so you don't see the chip model. So you do like analysis of this binary code, and you detect the CPU, ARM, MIPS, PowerPC, and so on. And then what you do, if you know the CPU code, and maybe you're lucky there's also some PHP files, what you do is you just take all these files and you run static and dynamic analysis, provided that you have static and dynamic analysis tools. Some people write their own scripts, like for IDA Pro. Some people just use existing tools. There are not so many open source tools, but there's some choice there, not very big. So static and dynamic analysis, and then a lot of manual intervention. We want to count the manual intervention maximally, but I'll talk a little bit later about this. So once you perform this static or dynamic analysis or manual analysis, you also look at the board if you have a device. You try to find the UART console, you find the debug interfaces like JTAG, UART, serial console. All the Linux kernel, for example, if it's a Linux-based device, you find all the Linux kernel boot parameters, like which offset to load the image, which are the partitions to mount, which type of mount you need to use, and so on. So basically, you know all these long strings of boot parameters. And of course, you also look for obvious known vulnerabilities. You go to the CV database, for example, you have a D-Link router. You go to the CV database, look for D-Link, and you see, oh, UPnP, daemon port 32,768. Okay, let's look. There is binary UPnP code. Okay, maybe it has like a vulnerability. You try to emulate it with a QEMU, or you try just to load it into IDA Pro and statically kind of know if there's the vulnerability, the backdoor, or the command execution, and so on. Some vulnerabilities, of course, you don't know they exist, and that's why you also need some kind of heuristics and some kind of tools like static analysis and dynamic analysis. Then, for example, if you are in my case, or you want to do it large scale, where you start without devices, what you do, you really want to confirm that what you found is really a vulnerability and it works on a real device. So you go and buy the device. Then it takes some time, it takes some money, more importantly. Time, money is the same, so time and money, so it's money. When the device arrives, you need to set up it. Set up meaning is, okay, not all the devices are like plug and play. Yes, they are plug and play, but then there's the switch, there's like all the connection to your Wi-Fi, all the Ethernet. And if, for example, you want to fuzz your device and it crashes and it hangs, you don't have a robot which unplugs. You have to do it manually. And if you have 10 devices, you need to go and unplug 10 devices. And if you have millions of devices, I don't see how you can do this, like you cut the power and so on. So setting up the device is also not trivial. And when you get the device, let's say you found a remote code execution, or you found, for example, a backdoor, and then you want to look for more, maybe there's some more. Let's open the device and find a serial port. Maybe I can get some more logs and actually get a root privilege, or like a boot injection of something. And you need to disassemble the device. Now, disassembling the device is like hardcore problem to solve automatically. I mean, manually it takes days, but if you have a robot, I don't think how they can figure out which device is which and how to unscrew all these things and not break the device. So you can obviously see in this diagram is like very obvious that this is like dealing with a physical thing is like an open problem. It's really hard to automate. Like to buy it, how do you buy the device? There are different kinds of hardware versions. Is it the right one? Is it the one which is related to the firmware you analyzed? Then you need to buy it. You need a lot of money. If you have hundreds of thousands, it's like a billion dollars project. Then setting up the device, again, as I mentioned, is not easy, and so on. So you see, this is a really hard problem to automate. However, if you look on the other hand, the first part is like when you start with a firmware with no devices, like the approach which I love to take and which I was doing for the last 3 years is you can clearly see that these are easy to automate, right? You just take the firmware, run the unpack, it unpacks, you find some files, you run some tools on these files. If you are lucky or your tools are very good or a combination of both, you get like remote code execution, XSS, backdoors, and plain passwords or default passwords, and everybody's happy. You find vulnerabilities, you can patch them, you can disclose them, and so on, or exploit, but hopefully not. I see a lot of black hats, so I think you exploit. So the idea is like to perform large scale and automated. So you basically, we want manual intervention at minimum to do what? To understand the firmwares, like what is inside the firmwares, how they are like operate, what is the usual, what is the majority of formats for the firmware? Is it a Linux based? Is it ARM or MIPS? Is it JFFS2 or Squash file system? Why you want to know these things? Because if you know that 80% of firmwares are Linux based and they use JFFS file systems and they run ARM, of course you'll focus to improve this kind of tools because it's 80%. That's why you kind of need to understand what is inside, and that's why you need to understand, classify, and afterwards analyze with new tools or improved tools. And more importantly is like without using the devices, because you stumble on very hard problem to solve automatically. Because you find, let's say, vulnerabilities in 1,000 devices, you cannot buy all of them 1,000. And when you are sitting on some vulnerabilities which you are not sure what to do, you go on Shodan, you can verify them on Shodan, but it's borderline legal and you get to jail just because, right? It's not good. So there's like a large number of challenges associated with this kind of research where you want to do large scale, thousands of firmwares, many devices. Is you have large number of devices, as mentioned, large number of firmware files. You also find a lot of heterogeneity in these devices because these devices have various kind of constraints. Some of them as smart cards or RFID cards, very small, specialized system on a chip or ASIC processors. Some of them are very generic ARM SDK, which you can buy from China. So there's a lot of heterogeneity in like hardware architecture, software architecture, software SDKs. Also, the data is very unstructured. It's not like you go to Google and you ask, give me an XML of all the firmwares. Not even Google knows that. You need to go at every site, including very obscure small manufacturer shop in Asia, not to say a particular country because it's kind of, yeah, and everything is in Chinese. You need to figure out what is what, and if it's a firmware or it's a driver or it's just a PDF or a zip with something you don't know with malware. And it's like very unstructured data. You need to figure out what is what, and then you need to find and correlate this to the billions of devices. If you're running like an enterprise network with tens of thousands of devices, printers, VoIP phones, you need to figure out, is this vulnerable or not, because you don't want to cut them off. So you need to kind of also know how to correlate vulnerabilities from the firmware to the devices. So we came up with some solutions during these years. So to address the large number of devices, we do the analysis without devices. That's the whole idea. I repeat it, but it's like one of the key drivers of this kind of research, without devices. And I'll go down later what it means and what it implies and what are the limitations, but nevertheless. Also, the large number of firmware files, you have hundreds of thousands, is like you want very scalable infrastructure. You don't want like a very sequential infrastructure. You just want to throw tens of thousands of firmwares in Amazon Cloud, or if you have a very powerful server at home, you just throw them in 1,000 virtual machine, you go to sleep, in the next morning you wake up, you get a report, 20 remote code execution, you drink your coffee, you are happy. So you need like scalable architectures. You cannot just write, small hackish things which you need manual adjustment every now and then. Because of the high heterogeneity of devices, is you need generic techniques. You cannot write a technique which works just on a given platform or a given processor or a given operating system, because if tomorrow the vendor updates the processor, changes the processor or the operating system, you need to rewrite your technique or the tool again, and it means manual work, and this development work is again not scalable. So ideally you want to find a generic technique or a generic approach to find these kind of vulnerabilities without reinventing or rewriting the tools. And there are some other challenges which I'll skip a little bit, but you can find them detailed more in the papers. So the first challenge is the firmware and device classification. So you have a lot of devices on your intranet as a system admin, or on the internet as a pen tester, red team, hacker, any kind of a camp you are in, from Shodan or these kind of tools, or your own Zemap. scans. And you have also a lot of crawlers which downloaded you hundreds of thousands or millions of files from the internet, and you have no clue what is there. You just really hope that they are firmwares, but you really have no clue. So how you approach this kind of big data? Well, I think the most obvious is to do machine learning. And yeah, what we did for some of our experiments, we use scikit-learn. Maybe you use something else. You develop your own kind of algorithm or frameworks for the well-known algorithms. We are not machine learning guys. I'm not very machine learning, but I try to learn machine learning for this kind of experience, and it's really interesting and it really helps. The idea is that, yeah, for machine learning, you need like to choose an algorithm, like SVM, support vector machines, random forest, decision trees. So basically, these are some techniques to sample some data and to train kind of artificial intelligence engine to kind of detect the new samples. So in our case, we tested random forest and decision trees. It was easier to use, and the API was better, and it was faster, and so on. SVM is good, is older, but it has some limitations. So then what you need to train for machine learning, for example, you need to train for features, what exactly to look for in a given object. And in our case, an object is a file, is a firmware file. We are looking for firmware files. And what we want to train machine learning is to say, hey, look at this parameter and this parameter and this parameter of the files. And these are the common characteristics of firmware files from this vendor. So we use, for example, file size and entropy value and strings. And I give you an example why I use this. For example, if a vendor has a flash of 4 megabytes, for example, for storing the firmware or file system, then most of the firmwares uncompressed from the zip, like the raw file system, will have more or less 4 megabytes, plus minus hundreds of kilos, right? But the idea is that it uses the hardware at maximum. The other vendor will have a 60 megabyte flash. So most of the firmware for that device will be 16 megabytes. So file size is one key characteristic to differentiate between firmwares of different vendors or different devices, because it's hardware driven. The entropy value is interesting. Basically, is kind of the number of useful information per byte. Is expressed as bits per byte, or there's more explanation for that. But the idea is that if it's a compressed file system or is an encrypted, you have a high density of information per byte. So you have 7 bits per byte of useful information. If it's a raw file system, like a dump of a flash from development board and to just upload to the device, you'll have like not very compressed. So you'll have 4, 5 bits per byte. And this can differentiate, again, different kinds of vendors, because one vendor chooses to use a compressed file system and the other vendor used to have a simple image of a file system. And the strings is obvious because, for example, if you are D-Link, of course, you'll have a lot of copyright D-Link, D-Link this, D-Link that. And these strings are useful to say, look, if you find D-Link strings number of time in this file, in this firmware, most likely is a D-Link related. If you find, let's say, TrendNet string so many times in this firmware, then most likely is a TrendNet. It's like common sense property. So we use a combination of these. We play with like both algorithms, and we kind of try to use different parameters for machine learning to see where is the optimal thing. So this is just an example, and I'll give you a reference to the paper. But the idea is that you see that on your left there is a curve which goes very well to 100% and very fast. So basically, this is the most optimal combination of features and algorithms we found, where basically, for example, if you have two vendors, right? Let's say 2 vendors, and both of them have 10 firmwares. Like you get 10 firmwares from one side and 10 firmwares from another side, and then you train your machine learning with the size, entropy, strings, and so on. And you use for training, you cannot use the entire set for training because you need to use just a small part so you can detect the unknown things. So from 10 you use 4 firmwares, and 6 you leave as unknown, and you use 4 from another vendor and you use 6 as unknown. Then basically this is the 40% training set size, and you see that using the blue curve is like random forests. The machine learning is able to say with more than 90% accuracy that one of the other six is this vendor. So it's able to accurately tell you, yeah, I know, I think it's most likely this firmware I just downloaded from the internet automatically, most likely is a trendnet because machine learning. So yeah, this is the local optimum. There is no rocket science, it's just experimentation with different features of the firmwares and finding the optimum. So why it's useful? Because you want everything automated. You have crawlers which go on the internet every now and then, or you collect files from people, and you want to automatically know it's a D-Link, it's a trendnet, and then apply particular tools or vulnerability tests. If you know that D-Link have this vulnerability in UPnP, for example, you want to, and you know the firmware is D-Link, you test the UPnP with Metasploit and say, yeah, okay, test passed, you check the box and you go next. The next thing is the automated static analysis. So the idea is that this is actually the first thing which we did. So the machine learning experience came as a retrospect because you learn by mistakes. You need to think about big data and do machine learning first and then go collecting thousands of files on the internet. But we did the first thing, just let's collect everything. So we collect everything and then we have like a combination of analysis cloud, like in our university, plus some Amazon nodes. And this is pretty simple. We do on every node, we just send the firmware and say, please unpack it with all known tools you know, and please do some static analysis. And also, if you can do also, and you find some hashes in the etc password, can you please send it to this machine which has NVIDIA Tesla? And can you break it very efficiently and fast so we know if it's a default password or not? And then we kind of use our information like library versions and so on to know more about the firmware and the operating system and so on. And we put it in a database. It's very simple architecture. It's not. So the type of static firmware analysis we perform, we check for misconfiguration like web server configs. For example, light HTTPD conf or boa.conf, you have like user equal root or user equal 0. Well, it's obviously a very bad misconfiguration. You don't want your web server on an embedded device to run as root, because once you get buffer overflow or command injection, you are root on the device, and it's not a good thing. We've seen some people running as nobody or dub, so it's kind of an improvement, but not so often. Most of them run as root. We also check for credentials, like we check the etc password, we check for Git repositories, we check for these kind of things, because there's a lot of leftovers, and you'll see this in many other talks or blog posts, that there's a lot of leftovers in the firmware. They just don't clean it up properly from the development to the production. So they ship it, basically the development version. Then we also use the versions and keywords. For example, you'd be surprised if you search the keyword backdoor, how many times it appears. Apparently there are like classes or files which have these backdoor capabilities, like in plain text. It was really surprising. And then we use the strings from the libraries and the file names. So we know, let's say, if it's OpenSSL 97A, oh, maybe it's vulnerable, because just by knowing the number or the name doesn't mean that the library was not patched. Maybe it was patched and it's not vulnerable, but at least you have a good starting point that, hey, there is like this vulnerable library, you want to check this first. If it was patched or it was compiled in a way that makes it invulnerable, it's good, but maybe not. Okay, and then we use correlation across firmwares, and that's where the big data set comes into picture. And the idea is that if you have one firmware from one device, and you find it's your home router, and you find the command injection or XSS, for example, and you say, hey, I found this, but then your neighbor says, yeah, I don't have this vendor. My vendor is vendor B. I'm not vulnerable for sure. But the idea is when you have so many firmware files, you can basically correlate. And even in devices which are kind of unrelated by brand, the idea is that sometimes they use common SDKs, which actually is the root cause of a vulnerability. The SDK come with a vulnerability, or they do not patch it, and so on. So in one example, and I'll show you like a small demo afterwards, we had one firmware from Wi-Fi SD cards, you know, like the small SD cards you put in all the photo cameras, and then the old photo camera is able to connect to your wireless router and sync your photos and so on. So basically it makes any camera intranet and internet connected in a way. So it was from Transcend, and the idea is that there was a public vulnerability in it. We found a couple of more afterwards by doing some more analysis. But the idea is there was a file which allowed like XSS and more importantly command injection. And there's like a huge blog post from the person who found it, how he manually did it and how he soldered and how he made the serial port and how he logged in and found so on. So the idea is that once we had this vulnerability, we kind of tried to find other firmwares which are kind of similar to the first firmware by size and by file structure and so on. And then we use the fuzzy hashing. How many of you know or use fuzzy hashing? Okay, there are some forensic people, I guess. So basically, fuzzy hashing is like crypto hash. If two contents are exactly the same, the fuzzy hash is the same. But if you put like a minor change, then the crypto hash is totally different, like the basis of MD5 and SHA-1 and SHA-256. For fuzzy hash is basically if you have two files which have slight difference, it will say that they are similar. It will produce a much bigger hash, and that hash is able to tell you that there is just some modification of between two files, but the files in general are similar. And this can be used to track like similar source code files or similar binary files, or it's used for binary malware correlation and so on. So what we do, for example, what we use fuzzy hashing in all the files we extract from the firmware, because there's a lot of files. We produce the crypto hash and the fuzzy hash, and then we kind of try to find which file is similar to which file from different firmware. So for example, in this case, we found that a firmware 2, when we unpack, there is a file which is hypothetically 99% similar to the file in firmware 1. And this 99 is not an exact number because this threshold might vary and is not an exact, like there's a 1 bit or 1 byte change, but you get the idea that there's kind of an empirical value behind this similarity. It's not like very strict. You can check the papers of the fuzzy hash and understand why it's like that. But the idea is that once we know that in firmware 1 there is a vulnerability in this file, and this file is similar 99 and 95% to other files, right? We can more or less safely assume that the other firmwares are also vulnerable, right? And we can kind of focus on those firmwares and those particular files similar and try to confirm that other firmwares and vendors are vulnerable. And actually we've been able to find this example with 95%, and I'll show you an example where we found a firmware from another vendor, actually, which is prone to similar to that exact vulnerability. And the reason why is because there is an Asian company which produces the SDK and the white label products. The white label is like a development board which comes as a white box, and there are two vendors, one in Europe and one in US, and they put different labels. But in essence, it's the same box, it's a white label. That's why it's called white label. You put any label you want, but it's the same product with the same vulnerabilities. So you can say, hey, actually you're also vulnerable too. So it's very important because sometimes devices seem different, but I'll show you other examples. And this one is another example. We do also correlation by HTTPS. For example, many of the firmwares contain the HTTPS certificate because maybe they provide also HTTPS web interface. Long story short, the idea is that many vendors use self-signed certificates, and when they generate the self-signed certificates, they also, for some reason, I guess also the sloppiness, they leave the private key of used to generate the certificate and to sign it. They leave it exactly in the same path with the certificate. So we found like 110 HTTPS private keys. So in general, if you have HTTPS private key, you can do man in the middle, or you can eavesdrop and then replay and decode all the communication. So if you are thinking that you're connecting through HTTPS to your home router and type admin and super secret password, guess what? I mean, it's not that super secret, even though it's HTTPS. So we found one such certificate. I just give you an example in a firmware, and we look it in the database, and we found it's a vendor A. And okay, we put it vendor A, but I'll tell you the name. The idea is that it's a Bricom, and it makes a difference because I show an example. And then when we did more analysis, like manual and some tests, some dynamic tests, we found that this vendor A actually has a vulnerability, which is kind of a, well, backdoor command execution was like a very complicated one. Then we use the ZMap results. Somebody knows ZMap? So basically, ZMap is kind of a super powered Nmap in a way that it is able to scan. If you have a 10 gigabit internet connection, it's able to scan the IPv4 space in like 1 hour. So it's really fast internet scanning. So if you want to scan for HTTP certificates, you just start it. In 45 minutes, you have all the HTTPS certificates from IPv4 addresses. And the idea is that they run this ZMap scan on different ports like SSH, Telnet, web interface, and HTTPS interface. And they build what is called the HTTPS ecosystem infrastructure. So if you go to zmap.io, you'll find all these scans. And basically, you'll find all these all these scans they perform daily. And the idea is that we have the certificate from the firmware, and we look it up, its fingerprint, and we actually find it, the fingerprint from the file in the firmware, we find it on the internet. So basically, the idea is that it's not a problem if the firmware comes with a certificate inside it, as long as the device regenerates the HTTP certificate on the first boot or is able to overcome. But our surprise was that we found that certificate from the firmware file is actually used on devices live on the internet. So it means that the private key we have in the firmware file can be used to actually attack or compromise devices on the internet. So another surprise was that when we look randomly for some of these IP addresses, we find that some of the IP addresses open an interface for vendor B device. It was not exactly the same device. So again, it was like a white label product where two CCTV manufacturers, they buy a white label CCTV camera. They put two different labels, but if you look in the internals, they use the same URIs, and they use the same HTTPS certificates. And guess what? If the first has a remote code execution or things like that, most likely the second has as well. I mean, there's easy to connect. Maybe it's harder to test, or you need to have both devices to confirm 100%, but 99.9% is the same vulnerability. And to summarize, just for one certificate we found, and one vulnerability, we found two different vendors. There might be more for this particular certificate. And at the time when we did it, it was like 35,000 online devices. And basically, we have in total around 110 private RSA keys for HTTPS certificates. And this list still grows every time we get a new firmware. We just get a new private key sometimes, and we just keep looking for them. And I'll just show you very quick demo. I mean, it's kind of a proof of concept, but the idea is simple. So the idea is that we have this kind of we have the file system of this device. You can see it's like file system with bin, and it has like busy box. Everybody's familiar with the busy box. It's kind of a compressed user space in one binary for usage in embedded devices. And there's a lot of like firmware upgrade and flash copy and flash erase. So it's like a embedded device firmware which we unpacked. And inside this, you also see all the versions of the libraries which I was mentioning. That's why it's interesting to collect them and so on. But the idea is that this file has these two files, which is called cert server certificate and private key server. Okay, so if we do both, one is a certificate and one is beginner, say, private key. So it's a private key, and very interesting is like without passphrase, because when they boot, there's nobody to type a passphrase. So their passphrase empty, and usually if there is a passphrase, the passphrase is somewhere in the file system because it needs to take it from somewhere. I'm sorry for that. And the idea is that like if we check the fingerprint of the certificate, we see it's a A2114E and so on. And if we check their modulus, the modulus B7, 3B, and so on is for the certificate. So basically the idea is that if a certificate and private key has the same exponent and same modulus, basically it's a glove match. It's one for another. One is used for signing and generating the other. And we see that for private key, we also have the same modulus. So basically it's a confirmation that this private key is the one used for this certificate. Okay, so we have a confirmation we have the right private key, and we can do bad things, but what is wrong, right? So the idea is, let's say we go on Shodan, and I already did it for you, but the idea is that okay, I just want to show you. Yeah, if I take all the details of a certificate. You see that it's Brickcom Corporation. So basically it's a manufacturer which is called Brickcom and so on. But the idea is, okay, it's no problem, it's a Brickcom. We go to the Shodan, and I just make a shortcut for you to show that it's vendor B. So I know already the name of this Promelit. And if you look for Shodan for Promelit, for example, is also a CCTV camera. Is from Italy, is most used in Italy. So in Italy they sell it as Promelit, in other places as Brickcom. And when you look, wow, there is a SSL certificate, but the common name is Brickcom, right? So, wow, it's kind of suspicious. So, if you go to this IP, now we'll not do anything like unauthorized because we don't log in, but I mean, it asks you something, we just cancel, we don't want to see anything from you. But you see that it says it's a Promelit device, okay? Then we go to HTTPS certificate, it says cannot connect securely because it's a self-signed. But if you go to the details, we'll see that okay, I'll just use the secure. So if I use the OpenSSL command to show the certificate of this particular IP, right? Then it will give me the Brickcom, and I can cut the certificate. So basically this is the certificate which is proposed by the device to me, right? So I take it, I put it into online cert. I mean, it's very simple, but I just want to show you. It's easy to automate, but the idea is to show. So let's see now the SHA of the certificate from the online. And the SHA is the same, A2114E. If you go up, then you'll see that the fingerprint is A2114E. So you can clearly see that these devices basically correspond to this thing. And now if I find a vulnerability in one of these files, most likely it's applicable to this device as well, even though it's from Promelit. Okay, so you see like how easy it is to correlate and why correlation is useful. So it was one of these kind of examples. I'll try to go on. So the idea is that we found like 38 new vulnerabilities by doing these simple things in around 700 firmware images, and we correlated some of these vulnerabilities to around 140 devices, like through HTTP certificates, through some other techniques. We correlated to this huge number of devices. Then static analysis is nice, but static analysis is like not very confident, right? It's because you just know some hints, but you don't know exactly everything, and that's why you want to do dynamic analysis, because it's actually executing the thing. I think we have 10 minutes, something like that. Yeah. So the idea is that we want to do this dynamic analysis also very fast, large scale. And what we use the unpacked firmwares, which we already done. We want to select some of the firmwares in a specific way. For example, if we want to test web interfaces, we want to select only the firmwares which have web interfaces, right? To perform dynamic analysis. But your criteria might vary. You might want to select devices to test for UPnP. Then you need to fix a little bit of the file systems, because sometimes when you unpack the firmwares or you do some stuff, the files break or the unpacker tools have bugs and so on. You need to fix the etc password and some other things, but this can be automated. And then what you do is basically you again do this in a private or Amazon Web Cloud, and you do dynamic analysis. And then you collect the results of the dynamic analysis from the tools, like the XMLs or the reports or the logs, and then you use this to improve the next time you will see similar kind of images. Now the big question is how you actually perform dynamic analysis on a firmware without the device, right? And the obvious answer is emulation. You need to emulate the firmware, and the most common answer to this problem, at least in open source community, is to use QEMU. This is what we used as well. And now, if you want to emulate, you have more dilemmas, because there are multiple ways to emulate. It's not just one way. It's infinite number of ways to do things. So there is the ideal emulator or perfect emulator, which can emulate from the firmware itself, can emulate any device, any peripheral, and can basically bring up an emulator which is 100% equivalent to the device, but it doesn't exist. At least not in public, and if it exists, most likely it costs very much. Then there is the original firmware, which I described, and using the original kernel, which is a little bit problematic, because the original kernel is not always delivered with a firmware update. Usually when you get a firmware update, it's either only the user space, the file system, or only some files, because it's a partial firmware update, because they just fix some files. So you very seldom get the original kernel, and to get the original kernel, you need to go with a JTAG to the device, which means manual steps, which means not scalable and hard and error prone. So this is also not quite a go. So the original firmware with generic kernel, basically you build a kernel for ARM or MIPS or all the architectures you want to support, and you build basically all the modules in it, and you hope that the device you want to emulate will hit on those modules. There's some other experimental thing, and I'll leave you to check the paper, because yeah, the time is a little bit short for me now. But then the final thing is that, for example, depending on the application you want to test, and it applies very well to web application, is, for example, if it's a PHP or Perl application, you don't need to emulate sometimes. You just can take the web root, document root, from the firmware, and you put on your Linux system in your document root, and you try to test. Sometimes it doesn't work because it needs some configuration file which is only in the firmware or device, and you need some manual steps. But the idea is sometimes you can kind of transplant the application to be tested into a hosting environment. So basically you host it in a separate environment. So in our case, we had to cross some of the options. So we don't have a perfect emulator, and we don't have time to build it. Then we don't have too many original kernels, so that's also a no-go. And that was too experimental for us. So we stick with two approaches, and I'll try to demo them. And the emulation accuracy and complexity and speed varies according to these arrows, and is not completely linear because, yeah, dependency. The idea is that how we do emulation, we have, let's say, a virtual machine, which I'll show you in a minute. And inside it, we have a QEMU. We are not saying it's the best thing, but we found it to be optimal. And apparently, some other people are also doing it this way. We found out recently. So I think it's kind of a common sense choice. It can have some small variations. So we use the QEMU, which was, we have like a stock of them for MIPS, ARM, PowerPC, Alpha Deck, whatever, all kinds of weird CPU architectures which can be there just to be prepared in case we hit on some kind of a firmware like that. We can just try to emulate it. Of course, the best support from QEMU is for ARM and MIPS, is more mature and stable. Then we use some Debian precompiled distributions, which are available online, and there's a kernel and a user space, so you get all the utilities like, you know, wget, curl, and all the utilities you need to do some scripting. Then what we do is just throw the firmware inside this QEMU, and then we do chroot. How many of you know or use chroot? Okay, so there's quite some people. So basically, it's kind of changing the root of the file system relative to some other point, so you can kind of have multiple root file systems in a single file system and you jump through them. And since for example, in our case, if it's a ARM firmware and we put it inside the ARM QEMU and everything is Debian ARM compiled, then chrooting is just perfectly fine because everything is ARM inside that QEMU, and there is no problem of not being able to execute and so on, right? Then what we do is just we call the normal, mostly it works for Linux-based systems, and there are pitfalls for binary blobs, but we do the init thing, and then we hope that all the applications and other network services start, and actually it starts pretty not bad. And then we just focus on the web server in our case. And we use the open source tools like Arachne, Zap, TCP dump. TCP dump, we record the communication so that we are able to track the inputs to the exploits easier, or to the thing triggering vulnerability. But you can also use the Metasploit and Nessus to test for known, or to fuzz with other tools. It's basically, there is no limitation. In our case, we focused on the web thing. There's some numbers, you can find them in the paper. I just want to show you the very quick demo in 5 minutes, so I'll not stress too much on these numbers, but there's a lot of numbers in the papers. Maybe you'll get confused. Don't hesitate to check with me. So the idea is that we have this virtual machine, right? Is a VM which we have like a template for that. What we do is just as mentioned in the figure, we just start the VM, we run the proper QEMU and throw the firmware inside it. And for example, in our case, the VM is running, you can see that the VM is running on this IP, okay, 248.132, and yeah, if I'm going to it, there is some kind of a page where I can drop a firmware, like as similar to our public site. And when I drop a firmware, there's some automated processes which take them. And one of the processes is just exactly to unpack the thing and start a QEMU and chroot and do all this stuff. And now if I SSH to the same IP but to another port, is like 2222, whatever. I mean, like it can be anything, right? I mean, port forwarding and so on. Basically, where I land up is land is the QEMU, right? Because we also map. I mean, in our approach, we kind of map this QEMU, the web port and the SSH port, to be accessible from the VM and so on. So now you see that it's a Debian ARM-L, and if I do uname, you see it's ARM v5v, and it's based on Debian 2.6 kernel, and so on. And basically, if there's also some, when we start the web server, we do some port forwarding for the web server, but you can do port forwarding for other services as well. And the idea is that there's port 80, and you can see it is a BOA, okay? And if I do BOA, you'll see that it runs from here, but it's basically from a CH root. It doesn't make any difference, but the idea it's running. So when I go to the IP address of the virtual machine, and you can think about this in a very scalable manner, but this is totally automated. What I show you is just like step by step, but all these IPs like can be public, private. You just go to these ports and you configure and you do everything, right? And the thing is that one of the things is I go to port 1180 and it says, oh, transcend Wi-Fi SD card. I don't have any SD card, you can see. So basically it's a web server which runs in the emulator and prompts me for a password. And you see I don't enter anything and it goes like that. One very quick test is that, you put the URL. It means that this firmware in particular has basically not enforcing the authorization. It asks you for a password when accessing the root URI, but when you go to direct URI, so it's one bug, right? I mean, you see how easy it is to find this kind of bugs and so on. Okay, let's just log in. It's usually admin. Sometimes you can find it by brute forcing with a good dictionary of about 100 passwords. You usually get it right. It's either admin or root or 1234 or 1456. And you see that the web interface is basically very well working. I mean, is pretty much working for what we want to do. We don't want to find, we don't have a perfect emulation. We know some things are broken, and we don't care to make it perfect, but we want to find the minimal number of bugs as quick as possible. And you can see that we can do some traversal, and there are some settings. And for example, if I do script alert, and I do submit, okay, it will be a little bit okay. So usually the dynamic analysis tools do this for us. But you see, you find a very simple XSS, right? And another one. So basically there are two fields which are poisoned with XSS and so on. You can find, if you go to our URL, another XSS in another page from the same input. And you can also see that there's the Arachne tool already did some kind of command injection test, and there's indeed some command injection. For example, if I go to firmware, and basically this is where the root tree of the file is, okay? And basically, if I search for command injection, which is kind of a pattern to detect command injection, you see that it also was able to basically touch some command injection into www.cgi and in TMP and so on. So you can see that you can easily find manually and also with the tools and so on these kind of bugs. And yeah, that was the quick demo. But I mean, I hope I kind of convinced you that yeah, is working and you can scale it. You can put firmware version 1, 2, 3, 4 into 5 virtual machines, do it in 5 minutes, and you are done with the entire lifespan of this device. You move to the next device. Okay, so I think there are some references I invite you to read, and there are some other tools which I invite you to explore and read about. These are basically the tools which we try to use, and most of them are open source. We try to give also the patches. These are my professors and some doctoral colleagues which we've been doing the work with, which I want to thank. And I thank the organizer. Thank you for the patience, and sorry for a little bit of delay. It's 1 hour, so I hope we can take 1 or 2 questions, but thank you.
I think we can take one question, if there is. No?
Just a very quick question. How you know which is the version of the kernel you need to use in emulation, since you said that the kernel is inside and you cannot access easily?
Yeah, so it's a very good question. I mean, this works in particular for Linux-based systems or like kernel-based systems, because for micro firmwares or binary blobs it doesn't work. But one simple thing is, I mean, you just do mod info, I think, on something like that, and then it will usually give you the version magic and most of the options you need, and also surprisingly some of them will give you parameters which you can use as a fuzzing input. So basically you can kind of use this kind of versioning. That's why I mentioned that we collect versions of kernels and tools and so on. So yeah, this, I mean, simple, everything is there.
Okay. Okay, then thank you so much for your presentation.
Thank you.